Welcome, AP Statisticians. We are on to Chapter 8. We're on the second chapter of Unit 2, and this should look oddly familiar. Hopefully, we're starting to get used to writing out our shape, outliers, direction, and strength, if we remember our SODs. So I've broken down the homework that I'm asking you guys to do over the 4 weeks. Make sure you're paying attention to the pacing guide that's posted on Schoology so that we are all on the same page. And then do note that we are breaking Unit 2 into 2 chapters or 2 tests. So we will have a test on Chapter 7 and Chapter 8, and then we will have a whole unit test afterwards. So let's just get into this. As many of you will be familiar in terms of talking about lines, and many of these will sound familiar, but there's a deep understanding that we need to do in order to grasp these least square regression lines. So the end goal is to determine the least square regression lines, or LSRL, describing the association between two variables. And what better way to start with an example? Now, many of you guys are applying to college, so this is really relevant to you guys. The following case study, SAT and college GPA, contains high school and university grades from 105 computer science majors at a local state school. Now, I'm going to ask you, describe the relationship. So if you break out shape, outlier, direction, and spread, we would say this is a moderately strong, positive linear relationship with few outliers that don't really change this being a linear relationship. If I told you that the correlation in the GPA is 0.7795, or we're saying R equals 0.7795, we can see that is a moderately strong relationship. And the strength of the correlation coefficient suggests a linear association between these two variables, but the correlation coefficient tells us nothing about the association itself. What we need to describe the linear relationship between quantitative variables is a model of that association. And so what we call that model is a linear equation that quantifies the relationship or pattern in the covariability of those variables. The model is the equation of the line that we fit to our scatter plot. Now I'm going to say this right off the bat. The linear model is nothing more complicated than a linear equation of a straight line through the data. That model will have a slope and intercept to help us understand and describe the relationship between the two variables. You guys have found slope and y-intercept since you're like in 6th or 7th grade. This is not new. It's unlikely in the extreme that points in a scatter plot of the variables data will actually form a nice straight line. But a nice straight line might suffice in describing the overall pattern of the scatter plot with the slope and y-intercept. If the relationship between variables is strong, we know that the variables tend to cluster to a line. And that means we can get some idea of the behavior of one, the response variable, by observing the behavior of another, the predictor variable, or the explanatory variable to the predictor variable. We can then make predictions about the response variable by knowing a value of the predictor variable. So what we need to do is find the equation of the line that best fits the data. That, of course, begs the question, what do we mean by best fit? And that's where we go into depth in this chapter. And that line of best fit is called the regression line, or more specifically, the least squares regression line. So first, off the bat, know this. The model will be wrong. That's not to say that our analysis is not worth doing. That's just saying that our model will not predict all of the actual values that we measure. It's a useful tool, but it's not a perfect tool. So what that means is the data points will rarely actually fall on the line. The model will predict a different value than the observed value, but it may be close and the model may be of great value, and that's what we care about. So similar to the way data values fall above or below the mean, think normal model, some points will be above and some points will be below the prediction line. And so we call the estimate made from a model is the predicted value, and that predicted value we write as y hat. And so we say y hat, and we denote it with a little hat on top of our dependent variable. Now, if we are above our line or below our line, then we are talking about the residuals. So the difference between the observed value, the actually measured term, and its associated predicted value, or y hat, is called the residual. To find the residuals, we subtract the predicted value from the observed value. So I want you to try to think of this. Residual is observed minus predicted. Now we use this letter E for residual. Now you might be asking, why don't we use R? Well, R is already taken in statistics. Remember, that's Pearson's correlation coefficient. So what's the next letter in residual? E. Or you can say the error in our model, the residual is the error measurement from the actual data value to what we predicted it to be. So think E for residual, E for error. Now let's get a little more into depth. Now, if you're following along with the notes in front of you, I do have a correction. A positive residual means the predicted value, the one in our model, is less than the actual model. And so if we have a positive residual, what that literally means, if we know that E is equal to y minus y hat, well, if our actual data value is above our model, then the residual will be positive, and our model is literally under the actual data, or it's an underestimate. Likewise, a negative residual means the predicted value is over the actual value, or an overestimate. So literally, if our data point is below our model, or the residual is negative, remember, y minus y hat is equal to the residual. If that's a negative value, then we are overestimating. Our model is overestimating our actual value. Por ejemplo, for example, in the figure, the predicted college GPA is 2.5. So if we go to 2.5, there's our model, while the true value of the GPA is 3.42, with a residual being 0.92, as you can do. Likewise, in the figure, the estimated college GPA is 2.8 over here, and the true value is 2.52. So if we calculated the residual, we get a negative 0.28, and we are seeing that is a overestimate of what the actual data value is. So we use residuals to see how well our model fits our data. So best fit equals least squares. So think what residuals are. Some are above the line, some are below the line. And some are positive, others are negative, and on average, they balance each other out. So this should sound very familiar to you guys in terms of calculation for standard deviation. So just like we did with standard deviation, if you recalled, we don't like the positives and the negatives, or going to the right or going to the, let's get rid of that. Instead, think back when we calculated standard deviations. We're going left and right of the mean. And so to get rid of the positive side and the negative side, we squared them. So just like we did with deviations, we square residuals and add the squares, resulting in this thing called the sum of squared residuals. This is also called the sum of squared errors, or SSE. Again, people will present that to you and think that they're sounding fancy. I want you to know that sum of squared residuals just means we're getting rid of the negatives. The smaller the sum, or least squares, literally, the better the fit. And the line of best fit is the line for which the sum of squared residuals is the smallest, the least squares line, which is where we come up with the least squares regression line. So this shows a least square residual line and visually demonstrates the methodology of least squares. The line that minimizes the residuals also minimizes the area of the squares. And I challenge you, if you click on this Desmos activity and you open it up into your browser, you're going to be presented with points in our line of best fit and see what's happening as we add in each one of these values. As we move our line to fit our data, what is happening to those squares? And note, as I pull my squares one way or the other, that blue line is the actual line of best fit. And if we are not there, then our squares get larger or smaller. So let's tie this back together. We're relating these residuals, these errors, and we're relating them with this standard deviation that we calculated before. And if we're calculating standard deviation and we're calculating residuals, well, why don't we look at z-scores? So this figure shows the scatter plot of z-scores for the variables of college GPA and high school GPA along the scatter plot of the raw scores. Now look, if we're looking at high school GPA to university GPA, we got their scores on each and we get our scatter plot. If we convert those to z-scores, what do we see? In essence, not in essence, they are the exact same graph. The only thing that's different is now where we can call this crosshair is where the two averages meet. So that is where Z high school and Z university GPA are the same. That's the averages. If you notice that they look exactly the same, that's because changing scales does not change R. That's from chapter 7. Please know that. Like, that's an important concept. When we change scale, the R doesn't change. Now, even more so, if we're just looking at the Z scores of the high school GPA and the college GPA, if an individual have an average high school GPA, we would expect about an average college GPA. That's at 0, 0. That's our origin. That also suggests the point consisting of the mean for each variable is on the least square regression line. So if you know the two means of each of your variables, that will most assuredly be on your least square regression line. That would tell us that moving one standard deviation away from the mean in X. So if I move one standard deviation in X, we are moving R times the standard deviation in Y. Sorry, moves us R standard deviations away from the mean in Y. Please put a star by this. The AP test loves seeing if you understand how you can move one direction horizontally and then how that is impacted vertically. And the verticality in z-scores is affected by R. So the correlation coefficient, R, Pearson's R, is the slope of the line of best fit for z-scores. Let me say that again. The correlation coefficient, R, is the slope of the line of best fit if we are using z-scores, meaning no units. That means that if the data have been changed to z-scores, the line of best fit fitting that data will have a slope of R. However, if the data is not re-expressed as z-scores, the slope of the least square regression line is most certainly not R. So this is a quick way, if we're just dealing with z-scores, no units, our slope will always be R, which is great to know. So what? As we close up this first video, so what? A slope of R, Pearson's R, for the line of best fit for z-scores means that a change of 1 unit in z sub x predicts a change of R units in z sub y. In terms of raw values x and y, a change in one standard deviation in x S sub x predicts a change in our standard deviations in y hat. Notice that x is the actual value, the input, and y hat is our predicted value, not our actual output value. So now what we can do is re-express the slope of the least squares regression line in terms of r. We've been dealing with it, that correlation coefficient, how strong the relationship is. We've seen, if I go back 2 slides, remember, this is how the calculator is calculating r for you. So we find the slope of our least square regression line is equal to r times the standard deviation of the y variable, of the predictor variable, of the response variable, divided by the standard deviation in our x, or explanatory variable. Or we could say r times s sub y divided by s sub x. So many times you're given a table and you're given the standard deviation in terms of your explanatory variable, you're given the standard deviation in terms of the response variable, and you're given r and you're asked to find the slope. This, I would put a note. I would maybe use this in your big ideas handout that I gave you guys. Please know this. Last 2 slides. Correlation and least square regression line. So now you know that a line that models our scatter plot of z-scores goes through the origin 0, 0, because that's where the mean of both of our variables is. And the slope of that line is r. Note in z-scores. So if we go back, and thus moving any number of standard deviations away from the mean in x moves us r times that number of standard deviations away from the mean in y. Remember, r is between -1 and 1, or the absolute value of r, the Pearson's correlation coefficient, cannot be bigger than 1. So each predicted y tends to be closer to its mean than its corresponding x. And this property of a linear model is called regression to the mean. The line is called the regression line. So that means if you've got a really high value the first time, chances are you'll have a lower value. As the more data you acquire, the values are going to get closer and closer towards the mean value, or regression towards the mean. I'm going to put the pause button on here. This is already enough as is. We're going to have at least 2 more parts going over all of the topics that you need to do in order to understand least square regression lines. So I will see you in the next one, Falcons.